In this problem, we'll use the stiffness method to find reactions for a coplanar or 2D frame. The key concepts we'll use are partitioning the structure stiffness matrix, calculating deformations for a frame, and calculating frame reactions given deformations. And here's our frame. It's determinate with a pin support at node 1 and a roller support at node 3. It's the same structure we used in the previous example where we assembled the structure stiffness matrix. So now in this problem, we're going to use that structure stiffness matrix, capital K, to determine the reactions. And here's our approach. We'll begin by finding reactions by using the equations of equilibrium. We can find the reactions that way because it's a determinate structure. And we've chosen a determinate structure so that we can evaluate how well we have applied the stiffness method to a structure where we can know the answer ahead of time. That's a prudent approach anytime we learn a new analysis method, be it by hand or by computer. Then for the stiffness method, we'll partition the structure stiffness matrix. Which we already assembled in a previous example. We'll find fixed end forces. Then we'll be ready to find displacements. Actually, let's call it deformations, because some of them will be rotations. 5, we'll find reactions using those deformations, and then we'll be able to compare our reaction results. Step 1. Let's find the reactions by using our equilibrium equations. And we have 3 reactions. Vertical reaction at node 1, which we'll call Q9 since it's in the degree of freedom 9 direction. Horizontal reaction at node 1, which is degree of freedom 8. And vertical reaction at node 3, which is degree of freedom 7. Let's begin by summing moments about node 1. I'll choose counterclockwise as positive. I get a negative contribution from the concentrated force, 5 kips. That acts through 12 feet, this height. I get a negative contribution from the distributed load acting over 12 feet. This length gives me the resultant force, and that's acting at a distance of 12 over 2 feet from node 1. Get a positive contribution from the reaction at degree of freedom 7, and that acts through this horizontal distance 12 feet. I solve that for the vertical reaction at degree of freedom 7, and I get a positive 17 kips. So it is up. And I solve forces in the x direction. I'll choose to the right as positive. I get a contribution from the reaction at degree of freedom 8. I have the applied lateral load of 5 kips. I solve that and find the reaction at degree of freedom 8 is a negative 5 kips, where to the right would have been positive. Now I sum forces in the vertical direction. I'll choose up to be positive. I have a positive contribution from the reaction at degree of freedom 9, a negative contribution from the distributed load acting over 12 feet, and a positive contribution from the reaction we calculated at degree of freedom 7. I solve that for the unknown reaction at degree of freedom 9 and obtain a positive 7 kips. It is acting up. Now just a reminder, these are not approximate results. These are exactly the results we should obtain from the stiffness method. Now step 2. Let's partition the structure stiffness matrix. And that's capital K. The reason we partition it is because to find the unknown deformations, we have to solve the following equation, where QK are the known loads, that is, the loads applied at the unsupported degrees of freedom, equals part of the structure stiffness matrix we'll call 1, 1. This refers to all degrees of freedom that are forces at the unconstrained degrees of freedom, and these are all of the unconstrained, or due to deformations at all the unconstrained degrees of freedom. We multiply that by the deformations at the unconstrained degrees of freedom, which are unknowns. We add in this portion of the matrix, which is forces at unconstrained degrees of freedom due to deformations at constrained degrees of freedom, times our known deformations, which occur at the constrained degrees of freedom. In this case, they're all 0 because there are no support settlements and no support rotations. So I won't need this chunk because it would just be multiplied by zeros. And we have to add in the fixed end forces in global coordinates at the unconstrained degrees of freedom. We solve this equation to find our deformations, and then we use that in the next equation to find our constrained forces, that is, our support reactions. And so we use this piece of the stiffness matrix. Forces at constrained degrees of freedom due to deformations at unconstrained degrees of freedom, so we need to multiply it by the unconstrained degree of freedom deformations that we will have just calculated using that equation. And this portion of the matrix if we have support settlements, but we won't need this portion because those deformations at the constrained degrees of freedom are 0. And then our fixed end forces at the constrained degrees of freedom. So even though it has a subscript u, we know what these are. We will calculate them ahead of time. So I need this chunk and this chunk. Both of them refer to the unconstrained degrees of freedom. And let's number all of our degrees of freedom on this matrix. They are in increasing order. And the rows the same way. And if we look back at our structure, the unconstrained degrees of freedom are 1, 2, 3, 4, 5, and 6. 7, 8, and 9 are all constrained. That's why we picked the numbering sequence we did, so that K11 would already be assembled in one corner of our structure stiffness matrix. And so I'll divide it in between the unconstrained and constrained degrees of freedom. Between the unconstrained and constrained degrees of freedom, this top left piece is the K11 we need. This bottom left piece is the K21 we will need. But before we can solve this equation for our unknown deformations, we need to calculate our fixed end forces. So step 3 is finding the fixed end forces. And we need that in global coordinates for the structure, so we need to find the fixed end forces in global coordinates for member 1 and add them to the fixed end forces in global coordinates for member 2. And I get member fixed end forces in global coordinates by using the transformation matrix, we'll call capital T, times the fixed end forces in local coordinates. And this expression is shown here in equation 16-5. This is the transformation matrix. Our fixed end forces in local coordinates, those are the fixed end forces that we get with the help of the inside back cover of our text. And then these are the fixed end forces for an individual member in global coordinates. So let's begin with member 1. I'll draw a free body of member 1 with the axial, shear, shear, axial, and moment drawn in the local positive directions, because this is the near node and this is the far node for member 1. Since there's no applied load and no applied displacement of one end relative to the other, all of our local Q's equals 0, which means that when we transform that to global coordinates, our 6 fixed end forces from member 1 are all zeros. But for completeness, I'm going to go ahead and label these. Our QNX is degree of freedom 8. The near node Y in global coordinates is 9. Then we need the Z, which is 5. Far node X is 1. far node Y is 2, and far node Z is degree of freedom 3. Now member 2. Draw a free body diagram. Member 2 is 12 feet long, has a uniform distributed load of 2 kips per foot. The near node is node 2, the far node is node 3, so the near node is at the left end and the far node is at the right end. We'll generate a QNY prime, a QFY prime from this distributed load, a QFZ prime, and a QNZ prime. In the X prime directions, nothing will be generated from this distributed load. So some of the information we'll need in order to transform it, we need to know that lambda x is plus 1, and lambda y equals 0, because the change in x coordinate is the same as the length, the change in y coordinate is 0. So we have these directional cosines. Now let's go to the inside back cover of our text to find our fixed end moments at the ends of the member. Our member resembles this situation. If we consider it fixed, it has uniform distributed load, and the fixed end moments are omega L squared over 12 at each end, counterclockwise at the left end, clockwise at the right, which means that QNZ prime for member 2 is going to be omega L squared over 12, because it's in the same direction as drawn on the inside back cover of our book. Omega L squared over 12, which is a positive 24 foot kips. At the other end, it's a minus omega L squared over 12, and so that's a negative 24 foot kips. Now let's apply equilibrium to this free body, and let's sum moments about node 3, the far node. We'll take counterclockwise as positive. We get a positive contribution from the left end fixed end force, a negative contribution from the left end fixed end force QNY prime, so positive from the moment, negative from the shear, and that acts through 12 feet. A positive contribution from the distributed load acting over 12 feet for the resultant, acting at a distance of 12 over 2 feet from node 3, and the fixed end moment at the right end, a negative 24 foot kips. Solve that for QNY prime, and we get a positive 12 kips. Then I'll sum forces in the vertical direction for that free body. This one here. We have the positive 12 kips at the left end, minus the distributed load acting over 12 feet plus QFY prime, the fixed end force at the right end, the shear. I'll solve for QFY prime and I'll get a positive 12 kips. And a reminder, with distributed load acting only normal to the member, QNX prime equals 0 and QFX prime equals 0. Now to convert these, which are in local coordinates, to global coordinates, we're going to transform it. And we said that lambda x is plus 1 and lambda y is 0. So this becomes 0, this becomes 1, this becomes 0, this becomes 1, 1, 0, 0, 1. And what we see is that the transformation matrix becomes the identity matrix when lambda x equals 1 and lambda y equals 0. The translation to that is when the local coordinate system, near to far, is the same as the global coordinate system, x, y, then there is no transformation necessary. The local fixed end forces are also in global coordinates. But let's assemble Q0 for member 2 here so that we can see it. And what we said is that they're already in the right coordinate system, or the same coordinate system as the global system, and so degree of freedom 1, this one, we said is 0. Degree of freedom 2, this one, is a positive 12 kips. Degree of freedom 3, this one, is Q and Z prime. Here we go. A positive 24 foot kips. Then degree of freedom 6, far x prime, 0. Degree of freedom 7, far y, plus 12. And 4, far z, minus 24 foot kips. We said that's 1 degrees of freedom, 1, 2, 3, 6, 7, and 4. And now for the structure. Remember, we said Q for the structure is going to be Q for member 1 in global coordinates plus Q0 for member 2 in global coordinates. So I'm going to write this out longhand, even though we know that all the contributions from member 1 are 0. And so now we'll work in increasing degree of freedom order 1 through 9. From member 1, Q0 is 0, 0, and 0 for degrees of freedom 1, 2, and 3. And for member 2, degrees of freedom 1, 2, and 3 are 0, 12 kips, and 24 foot kips. So for degree of freedom 1, we have the 0 from member 1 and the 0 from member 2. Degree of freedom 2, we have the 0 from member 1 and the 12 kips from member 2. Degree of freedom 3, 0 from member 1, and the 24 foot kips from member 2. Now degree of freedom 4, which is only attached to member 2, so we need only look at capital Q naught for member 2. And for degree of freedom 4, we had a minus 24 foot kips. Now degree of freedom 5, which is only attached to member 1, and we know that all of the capital Q's from member 1 are 0. Then degree of freedoms 6 and 7, which come from member 2, and we have 0 and 12 kips. Then degrees of freedom 8 and 9, which are only attached to member 1, but we saw that member 1 has all zeros for its fixed end forces for this problem. We'll add them up. 0 plus 0, 0 plus 12, 0 plus 24, and then we had the negative 24 foot kips, the 0, 0, 12 kips, 0, and 0. And I'll label our degrees of freedom so that we can find the parts we need more easily later. Now we'll also need, in order to solve for deformations, capital Q, not the fixed end forces, but the applied forces in global coordinates for all of the degrees of freedom for the frame. And this structure has only one force applied directly to a degree of freedom, and that's the 5 kips applied at degree of freedom 1. And so we have a positive 5 kips here, and then zeros for all the other degrees of freedom for capital Q. And this is the same degree of freedom sequence: 1, 2, 3, 4, 5, 6, 7, 8, 9. Now step 4. Let's find deformations. To do that, we said our formula looks like this. Times our unknown deformations, our deformations at unconstrained degrees of freedom, plus our fixed end forces at unconstrained degrees of freedom. Now to solve this for our unknown deformations, symbolically, we have the following matrix operations. We subtract the fixed end forces from the applied forces at the unconstrained degrees of freedom, and that makes a new vector. We pre-multiply it by the inverse of the K11 matrix, and we get our unknown deformations. Now, the most efficient algorithm for solving this system of equations is to not actually invert this matrix, but to use something like Gaussian elimination. But in this case, I have used a numerical method to invert the matrix and have provided it here. and it is in degree of freedom sequence for our 6 unconstrained degrees of freedom. And so to find our unknown deformations, we have to multiply this matrix here by the difference between these two vectors. So let's find that. And so we have qk minus qk naught. And for our 6 degrees of freedom, qk is this portion, because our 6 unconstrained degrees of freedom are 1 through 6, and q naught are these. So we have 5 kips, 0, 0, 0, 0, 0, and minus 0, 12 kips, 24 foot kips, and minus a negative 24 foot kips, 0, and 0. When we add all those together, we'll have 5 kips minus 12 kips minus 24 foot kips, a positive 24 foot kips, 0, and 0. Notice that our units here are foot kips, but our units up here are inches in kips. So we need to be consistent. Let's convert these. The 5 kips need not change, nor the minus 12 kips. When we take 24 foot kips times 12 inches per foot, we'll get a negative 288 inch kips, a positive 288 inch kips, a 0, and a 0. And remember, these are degrees of freedom 1, 2, 3, 4, 5, and 6. So we're going to take this matrix, multiply it by this vector, and we'll get a vector that is our deformations. Now when we do that, we'll take this term times the 5 and this term times this, etc., etc. But when we have the zeros, that means that no matter what these columns are, it won't change our answer because the Q's are 0. Oops, that's degree of freedom 6. So that simplifies our math a little bit. So let's write out the resulting equations. For degree of freedom 1, we have the first coefficient, 9.439, 10 to the minus 2 inches per kip, times the 5 kips, to which we add the 1.591 times 10 to the minus 4 inches per kip, times the minus 12 kips, to which we add the negative 3.283 times 10 to the minus 4th per kip, times the negative 288 inch kips, plus the 1.625 times 10 to the minus 4th over k, times the positive 288 inch kips. And then the rest of the Q terms were 0. So when we evaluate that expression, we get 0.611 inches. Now the next one. 1.591 10 to the minus fourth inch per kip times the 5 kips plus 1.655 times 10 to the minus fourth inch per kip times the minus 12 kips plus, missed that one, plus a negative 1.127 times 10 to the minus 6 per kip times minus 288 inch kips minus a 1.160 times 10 to the minus 6 per kip times the 288 inch kips. And when we put those together, we get a negative 0.001 inches. Now the next row. Negative 3.283 times 10 to the minus fourth per kip times 5 kips minus 1.127 times 10 to the minus 6 per kip times the minus 12 kips plus 2.326 times 10 to the minus 6 per kip inch times the minus 288 inch kips minus 1.151 times 10 to the minus 6 per kip inch times the 288 inch kips. And when we put all of those together, we get a negative 2.63 times 10 to the minus third radians. Now degree of freedom 4. 1.625 times 10 to the minus 4 per kip times the 5 kips minus 1.160 times 10 to the minus 6 per kip times the minus 12 kips minus 1.151 times 10 to the minus 6 per kip inch times the minus 288 inch kips plus 2.361 times 10 to the minus 6 per kip inch times the 288 inch kips. Put that together and we get a positive 1.94 times 10 to the minus 3 radians. Now degree of freedom 5 minus 8.191 times 10 to the minus 4 per kip times the 5 kips minus 1.094 times 10 to the minus 6 per kips times the minus 12 kips plus 2.257 10 to the minus 6 per kip inch times the minus 288 inch kips minus 1.117 times 10 to the minus 6 per kip inch times the 288 inch kips. Evaluate that expression, and we get a minus 5.05 times 10 to the minus 3 radians. And now our last unconstrained degree of freedom 6, 9.439 times 10 to the minus 2 inch per kip times 5 kips plus 1.591 times 10 to the minus 4 inch per kip times the minus 12 kips minus 3.283 times 10 to the minus 4 per kip times the minus 1 or 288 inch kips plus 1.625 times 10 to the minus 4 per kip times 288 inch kips. And if this looks familiar, it's because it's exactly what we had for degree of freedom 1. So again, we get 0.611 inches. And so these are our calculated displacements for degrees of freedom 1 through 6. Now step 5. We are ready to find reactions. Remember our relationship or equation for doing that. The forces at supported degrees of freedom equal K21, that is forces generated at supported degrees of freedom due to deformations at unsupported degrees of freedom, times those deformations at the unsupported degrees of freedom, plus our fixed end forces at the supported degrees of freedom. And I've pulled K21 from our previous slide and repeated it here. So if I scribble that out and write in QU, what we're looking for, degrees of freedom 1, 2, 3, 4, 5, 6. We need our 6 deformations associated with the unsupported degrees or unconstrained degrees of freedom, which we found right here. And so I'll rewrite them at 0.611 inches at degree of freedom 1, a minus 0.001 inches at degree of freedom 2, a minus 2.63 times 10 to the minus 3rd radians for degree of freedom 3, 1.94 times 10 to the minus 3 radians for degree of freedom 4, minus 5.05 times 10 to the minus 3rd radians for degree of freedom 5, and 0.611 inches for degree of freedom 6. And so our degree of freedom numbers here match our degree of freedom numbers for the columns, and that'll give us a vector of results that are the forces at degrees of freedom 7, 8, and 9 are constrained degrees of freedom. And that takes care of K21 and our deformations. Can't forget to add our Q0 for degrees of freedom 7, 8, and 9, which we had calculated to be these 3 quantities. So we have the 12 kips, 0, and 0. So now let's evaluate our first row for degree of freedom 7. We have this term times this term, which is 0. We have this term times this deformation minus the 5874 kips times this deformation minus 5874 kips times this deformation then our last two terms here are 0, so these don't contribute, but we do have a positive 12 kips. So when I multiply, add all of these up, I get a positive 16.1 kips. Now degree of freedom 8. This term times this deformation inches, and we have 0 times this deformation, and we have the minus 5874 kips times this deformation, degree of freedom 3, plus a 0 times deformation degree of freedom 4 minus 5874 kips times deformation at degree of freedom 5, which is a negative 5.05 times 10 to the minus third. Then we have a 0 times this degree of freedom plus a 0 from the fixed end forces. When we multiply and add all of these up, we get a negative 4.7 kips. Then we have, for degree of freedom 9, this term times this deformation minus the 6042 kips per inch times this deformation and the rest of these are zeros, so these do not contribute, and our fixed end force is 0. When we multiply these together, we get a positive 6.0 kips. Remember, these are degrees of freedom 7, 8, and 9. And now step 6. Let's compare results. From the stiffness method, we just calculated reaction at degrees of freedom 7, 8, and 9 to be 16.1 kips minus 4.7 kips and a positive 6.0 kips. Then from equilibrium equations, we calculated those same reactions to be 17 kips minus 5 kips and plus 7 kips. And these results should match exactly, but they don't. So the question why should occur, and the answer comes from a quick review of the calculations we performed. We inverted the K11 matrix, which introduces round-off error. Our calculations of the deformations involved adding and subtracting large numbers and trying to keep the remainder. That's called subtractive cancellation, and it introduces even more round-off error. And in our calculations for the reactions, we introduced subtractive cancellation again, which is even more round-off error. So I think it's reasonable to conclude we have properly applied the stiffness method, but what we have learned is that we probably need to carry more than 3 or 4 significant figures in these calculations if we want to keep our errors below 1%. Now let's go back and review the process we followed to calculate our reactions. We began by applying the equations of equilibrium to find the reactions so that we could compare our results at the end of our stiffness method analysis. We then partitioned the structure stiffness matrix, which we had assembled in a previous example, and we identified which pieces of that structure stiffness matrix we would need in order to find the deformations and then the reactions. We also needed fixed end forces for the structure in global coordinates. And so we started with member 1 and then member 2. We observed that we calculate the fixed end forces initially for the member in local coordinates, and then we use the transformation matrix to transform those to global coordinates. We then compiled the fixed end forces from member 1 and 2 to obtain the fixed end forces for the structure. And we also compiled capital Q, which is the applied loads to the structure. We then found the deformations by using the inverse of the K11 matrix. We noted that Q for the unsupported degrees of freedom had to be in the same units as the coefficients in the K11 matrix, so we made that conversion. We multiplied the matrices, evaluated the expressions, and obtained the deformations. We then used those deformations with the fixed end forces and part of the structure stiffness matrix to find our reactions. And we then compared the reaction results from the stiffness method with those results from applying equilibrium, and found that they were fairly close enough to suggest that we have properly applied the stiffness method, but far enough apart to suggest that we need to carry more significant digits through the stiffness method process, because the stiffness method process is susceptible to round-off error. Well done.